For most of human history, the night sky felt simple. Points of light. Fixed. Predictable. They rose. They set. They returned. Ancient civilizations mapped them into stories, into gods, into meaning. The sky was distant, but it made sense. Even when it frightened us, it followed rules we could see. Then we built tools to look closer. Telescopes stretched our vision beyond naked sight. Stars became suns. The Milky Way became a structure instead of a backdrop. The universe began to feel large, but still understandable. We discovered gravity, motion, cause and effect. There was comfort in it. Space, we believed, was a machine. Vast, yes, but orderly. If you knew the equations, you could predict the future. If you traced the forces, you could explain the past. The deeper we looked, the more confident we became. Then something strange happened. The universe did not become clearer. It became stranger. As telescopes improved, the sky began to misbehave. Stars were moving too fast. Galaxies were spinning in ways that shouldn't be possible. According to everything we understood, they should have torn themselves apart long ago. But they didn't. Something unseen was holding them together. We called it dark matter, not because we knew what it was, but because we didn't. It did not emit light. It did not absorb light. It passed through space and through us without a trace. Yet without it, galaxies could not exist. Most of the universe, it seemed, was made of something invisible. Still, this wasn't chaos. It was a mystery, but one that felt solvable. A missing piece, an undiscovered particle, a future breakthrough waiting to happen. So we looked deeper, and that's when space began to accelerate. Distant galaxies were not just moving away from us. They were fleeing. The farther they were, the faster they receded, as if space itself were stretching, pulling everything apart. Not slowing down, as gravity should demand, but speeding up, an expansion with no obvious cause. To explain it, we named another unknown. Dark energy, a force we cannot see, cannot touch, and cannot reproduce. Yet it dominates the fate of the cosmos. It pushes against gravity. It overpowers matter. It dictates how the universe will end. Together, dark matter and dark energy make up roughly 95% of everything that exists. Everything we can see, stars, planets, galaxies, people, amounts to the remaining 5. We had not uncovered the universe. We had uncovered our ignorance. The deeper we looked, the less we understood what space was made of. But still, the math worked. The models held. The equations balanced. So we pushed farther, beyond nearby galaxies, beyond clusters, back toward the beginning. We followed light that had been traveling for billions of years. Photons released when the universe was young, hot, and dense. We detected the faint afterglow of creation itself, the cosmic microwave background, a snapshot of the universe as it was, just 380,000 years after the beginning. And at first glance, it looked calm, uniform, smooth, almost boring. But hidden inside that faint static were tiny fluctuations, imperfections in temperature so small they seemed insignificant. Yet those imperfections would become everything. They were the seeds of galaxies, of stars, of structure. And here, again, the universe behaved almost too well, too smooth, too evenly balanced. According to our theories, the early universe should have been far messier. Regions should have evolved differently. Structures should have diverged wildly. They didn't. Something had flattened the universe, smoothed it, forced it into near-perfect uniformity. To explain this, scientists proposed a moment so extreme it defies intuition. Inflation. A fraction of a second after the universe began, space itself expanded faster than the speed of light. Not matter moving through space, but space expanding everywhere at once. Distances stretched beyond comprehension. Quantum fluctuations were blown up to cosmic scales. The blueprint of the universe was laid down in an instant. And then, just as suddenly, it stopped. Pause. Inflation explains why the universe looks the way it does. But it raises a deeper question. Why did it happen at all? What triggered it? What ended it? And could it still be happening, somewhere beyond what we can observe? The deeper we look into space, the more we rely on events we cannot see, forces we cannot test, and moments that occurred beyond any possible experiment. Our universe appears finely tuned, balanced on a knife's edge between collapse and emptiness. Too much gravity, and it falls back in on itself. Too much expansion, and matter never forms. Yet here it is. At first, space promised order. Then it offered mystery. And now, as we look deeper than ever before, it begins to feel less like a machine, and more like a question. In the next part, we leave the early universe behind, and confront a place where even the rules of reality begin to break. Black holes, regions where space, time, and meaning itself start to unravel. There are places in the universe where our language begins to fail, where distance loses meaning, where time no longer flows the way we expect. They are not objects in space. They are wounds in it. Black holes. At first, they were only equations. Strange solutions hidden inside Einstein's mathematics. Regions where gravity becomes infinite, and the known laws of physics collapse under their own weight. For decades, many believed they could not exist. They were too extreme, too absurd. Then we found them. Black holes form when matter is crushed beyond all known limits. When a massive star dies, its core collapses so completely that not even light can escape. Space folds inward. Time slows. The universe creates a boundary, an edge beyond which nothing returns. The event horizon. Cross it, and the future no longer includes the outside world. To an observer far away, objects falling toward a black hole appear to freeze. Their clocks slow. Their light stretches and reddens until it fades into darkness. But for the falling object, time feels normal, until it doesn't. Inside, gravity is no longer a force pulling things down. It is space itself dragging everything forward, toward a central point where density becomes infinite. The singularity, a place where equations explode, where time and space switch roles, where cause and effect may no longer exist in any recognizable form. We do not know what happens there, not because we lack data, but because our theories break. General relativity predicts singularities. Quantum mechanics forbids them. Both frameworks work perfectly until black holes force them to meet. And when they do, they disagree. The deeper we look at black holes, the more they behave like paradoxes. They have temperature. They emit radiation. They slowly evaporate. According to quantum theory, black holes are not entirely black. They leak energy, a faint glow known as Hawking radiation. Over unimaginable timescales, they lose mass. And eventually, they disappear. But this creates a problem. If something falls into a black hole, its information, every particle state, every quantum detail, appears to be lost forever. Yet quantum physics insists that information cannot be destroyed. Not ever. So where does it go? Does it remain encoded on the event horizon? Is it smeared across the surface of the black hole? Does it escape, hidden within the radiation? Or is information itself not as permanent as we believe? This is not an abstract debate. Information is the foundation of reality. It defines particles, fields, and the evolution of the universe. If black holes erase it, then the universe is not deterministic. Cause and effect are broken. The future cannot be predicted, even in principle. And space, at its deepest level, may not make sense at all. Then came an even stranger discovery. Black holes are not rare. They are everywhere. At the centers of most galaxies, including our own, lurks a supermassive black hole, millions or billions of times the mass of the Sun. These giants shape galaxies. They regulate star formation. They sculpt the structure of the universe on the largest scales. They are not anomalies. They are architects. And yet, we cannot explain how they formed so quickly. Some appear to have existed when the universe was less than 1 billion years old, far too young to have grown by conventional means. Something helped them, something we don't yet understand. As we look deeper, black holes stop being exotic endpoints of dying stars. They become fundamental. Some theories suggest they are connected to the fabric of spacetime itself, that space may be woven from quantum information, stitched together by entanglement, and that black holes reveal the threads. In this view, gravity is not a force. It is an emergent property, a side effect of deeper rules we have only begun to glimpse. The deeper we look into space, the more it seems that reality is not built from matter and energy alone, but from information. And black holes may be the clearest windows we have into that hidden structure. Yet even black holes are not the end of strangeness. Beyond them lies a universe that may not be singular at all, but endlessly repeated. In the next part, we confront a possibility that challenges meaning itself. A cosmos where our universe may be just one of many. At some point, the universe stops feeling large. It starts feeling excessive. Our observations suggest that the laws of physics are finally balanced, so precise that even tiny changes would erase stars, chemistry, or life itself. Gravity slightly stronger, and the universe collapses. Slightly weaker, and matter never gathers. This balance feels improbable, almost deliberate. To explain it, scientists propose a radical idea. Maybe this universe isn't special. Maybe it's just one outcome among countless others. The multiverse, a vast ensemble of universes, each with its own laws, constants, and histories. Some burn out instantly. Some never form atoms. Some are empty, silent, still. And a few, by chance, look like ours. In this view, the universe doesn't make sense because it doesn't have to. We exist here not because the cosmos was designed for us, but because this is one of the rare places where observers can exist at all. It is not purpose, it is selection. Some versions of inflation suggest new universes are constantly forming, budding off from expanding space like bubbles in a cosmic foam. Each bubble becomes its own universe, forever unreachable from the others. No signals pass between them, no light, no information. If this is true, then most of reality lies beyond observation, beyond science as we currently practice it, and that is deeply unsettling, because it means the deepest answers may never be testable. The deeper we look into space, the more explanations rely on what we cannot see, cannot measure, and may never confirm. The universe becomes not just strange, but incomplete. Are we uncovering reality? Or are we reaching the limits of what explanation itself can be? In the final part, we turn inward, to the question that remains when space stops making sense at all. When the universe no longer makes sense, we turn the question around. Not outward, inward. Because every mystery we have uncovered in space eventually leads back to the same place, the observer, us. For centuries, science assumed a simple truth. The universe exists independently of who is watching. Reality unfolds the same way, whether or not anyone is there to see it. But at the deepest levels, that assumption begins to crack. In quantum physics, observation is not passive. Measuring a system changes it. Particles exist in superpositions, multiple states at once, until they are observed. Only then do they choose, or appear to. This is not philosophy. It is experiment. Quantum uncertainty is not a flaw in our instruments. It is woven into the structure of reality. The universe, at its smallest scales, does not behave like a fixed story. It behaves like a set of probabilities. And space itself may be built from those probabilities, stitched together by relationships, not locations. Entanglement links particles across vast distances. Change one, and the other responds instantly, as if space between them does not exist. Not because information travels faster than light, but because, at a deeper level, separation may be an illusion. Some physicists now suggest that space and time are not fundamental. They emerge from deeper rules, much like temperature emerges from the motion of atoms. If that is true, then asking what space is made of may be the wrong question. The better question might be, what gives rise to experience at all? The deeper we look into space, the more the universe resembles a computation, processing information, evolving states, exploring possibilities. But computation requires a framework, rules, constraints, logic. Where do those come from? Even time, once thought to be absolute, begins to dissolve. In relativity, it stretches and compresses. In quantum gravity, it may not exist at all. Some equations describing the universe work perfectly without time. A universe where change happens, but nothing flows. No past, no future, only relations. And yet, we experience time intimately. We remember. We anticipate. We age. So where does time come from? From entropy? From memory? From consciousness itself? The deeper we push science, the more it blurs into questions once reserved for philosophy. Not because science is failing, but because it is succeeding. It has stripped away layers of assumption, revealing a universe that is not intuitive, not comforting, and not easily explained. A universe dominated by invisible matter, driven by unknown energy, governed by rules that fracture at the extremes. And yet, this same universe produces stars, chemistry, oceans, and minds capable of asking questions about their own existence. Perhaps the universe doesn't make sense in the way we expect. Perhaps meaning is not written into space and time, waiting to be discovered. Perhaps it emerges from complexity, from relationships, from awareness. The deeper we look into space, the less it makes sense. Not because reality is broken, but because we are glimpsing something larger than understanding itself. And the final question remains: is the universe strange because it is incomplete, or because we are only just beginning to see it?